Good morning, everyone. I am Nabasmita Fukan from the Department of Electrical Engineering, Indian Institute of Technology, Indore, Madhya Pradesh, India, and I'm going to present my paper, Fast Straightforward RR Interval Extraction-Based Atrial Fibrillation Detection using Shannon Entropy and Machine Learning Classifiers for Wearables. The outline of my presentation is as follows. I'll talk about what is atrial fibrillation in introduction, followed by the literature review and proposed method, results and discussions, and the conclusions. Then it is followed by the acknowledgement for the work and the references. Introduction. So what is atrial fibrillation? Atrial fibrillation is a heart condition in which the person feels rapid heartbeats, and this leads to him feeling dizzy or nauseous. But apart from that, it can also lead to ischemic stroke. And this atrial fibrillation is basically characterized by two measured things, that is RR intervals, that is the distance from one R peak, distance from one R peak to another R peak, and the absence of P wave. Here we can see that the RR interval from this peak to this peak is different from the RR interval from this peak to this peak. So this is a clear case of atrial fibrillation. Coming to the literature review, in the past studies, there are various AF detection methods that were proposed in literature, and using various machine learning techniques and signal processing techniques, but these atrial fibrillation methods fails to detect atrial fibrillation in case of human activity. So, or in case of ambulatory conditions, or when the person is under exercise. So so this is one of the reasons, or this is one of the motivation behind our work. Coming to the existing methods, there are five existing methods that we have taken into consideration. In these methods, different types of features like RR intervals, then different features extracted from RR intervals, or different methods like threshold-based methods, rule-based methods, machine learning methods, and deep learning have been used for detection of atrial fibrillation. Now, what are the limitations of these methods? As I have already said, these methods fail to detect atrial fibrillation under human activity conditions. So there is a need for a reliable AF detector in presence of activity. Also, due to this condition, it leads to false alarm, and we need to reduce false alarm in case of atrial fibrillation. Moreover, many of the wearable devices available in the market today do not have the feature of atrial detection, and in most of the methods reported in literature, the size of the detection models are not mentioned, or these have not been evaluated. These size of the models lead to a very important information, that is energy required to run the model. And in a resource constrained device such as wearable devices, we require a model which consumes less energy. So this is another thing that is not mentioned in the previous works. So what are the measure contributions of our work? The measure one of the measure contribution of our work is that we have proposed the amplitude independent QRS detection method using durations of ECG signals of segment duration 10 seconds and 30 seconds. And next, we have presented a single feature for detecting AF rather than using multiple features. And third is that we have proposed a low, fast, and robust AF detection method, which have been evaluated using 5 machine learning classifiers and on 2 unseen datasets, which are of different lead configurations, 2 lead and 12 lead. So coming to the proposed methodology, there are 5 blocks in the proposed methodology. The first is the QRS extraction, where we have 3 steps, that is windowing the ECG signal, then pre-processing the signal, and then suppressing the noise and extracting the QRS complex. After the QRS complex is extracted, we need to extract the RPIC, location of the RPIC. For that, we need to go through multiple steps like adaptive amplitude thresholding, smooth Shannon energy envelope extraction, adaptive Shannon energy envelope thresholding, followed by first order derivative and smoothing, and negative 0-point crossing detection, and lastly peak correction, and finally the RPIC detection. All these steps are included in the method so that false peaks are not false peak locations are not extracted by the method. And in certain cases, we see that even after first range of thresholding, the amplitude of noise is higher than that of the RP. So in such conditions, adaptive Shannon energy envelope thresholding helps in removing those noises. And sometimes in between too high noise, we may have a RP, and in those cases also, this method is very useful. Coming to feature extraction, we have, after the RPIC is detected, we go for RR interval calculations and heart rate calculation, and followed by the symbol sequence and the word sequence, and then Shannon entropy of the word sequence. These Shannon entropy is taken as features and fed to the machine learning classifiers, and we have used 5 machine learning classifiers here. And from these classifiers, we can detect whether that segment is an atrial fibrillation segment or a non-atrial fibrillation segment. Then the next figure gives us a rough estimate of the different steps involved in the RPIC detection method. As you can see, the first figure gives us the it's a figure of the 10-second ECG segment from MIT BIH atrial fibrillation database, which has been used in the training of the entire 5 models. Then the second diagram gives us the normalized QRS complex that is extracted from these previous signal. And this has been extracted using the Gaussian derivative kernel. Then we have the smooth Shannon energy envelope, and followed by number D, that is the figure that is a wave Shannon energy envelope obtained after thresholding. Then after thresholding, we go for smoothing of the Shannon energy envelope, and then we have the difference. Number F gives us the difference between the Shannon energy envelope, and then finally we have the detected RPICs and the true corrected RPICs. So next step that we after RPIC detection is the feature extraction, where we have the RR interval, which is the difference between 2 RPICs, heart rate, which is calculated by this formula. Then we have the symbolic sequence, which gives us the dynamic patterns of the which gives us the it gives us the instantaneous heart rate state. And then we have the word sequence, which gives us the dynamic pattern of the symbolic sequence. Then from this word sequence, we get the Shannon Shannon entropy. And Shannon entropy measures the information content of the heartbeat sequence. And this is given by this formula. Coming to the databases, we have 3 databases, one for training and 2 unknown databases for testing. For training, we have the MIT BIS atrial fibrillation database, which has been resampled to 300 Hertz. Then for testing, we have the long-term atrial fibrillation database and the China Physiological Signal Challenge 2018 database, which is also known as the CPSC 2018. This is also resampled to 300 Hertz. Now, each of these databases have different numbers of atrial fibrillation and non-atrial fibrillation segments based on the segment durations, which is given in this figure. So you can see that these represents the number of AF segments present in MIT BIS, LTAF, and CPSC for 10 seconds duration. This is the number of non-atrial fibrillation segments present in these databases. This is for 30-second duration, the number of atrial fibrillation segments present, and this is for 30-second duration, number of non-atrial fibrillation segments. Coming to the resultant discussion section, we have used three matrices: accuracy, sensitivity, and specificity to represent the outcome of our machine learning classifiers. And table 1 gives us the performance of the ML classifiers with 10-second ECG segments, and table 2 gives us the performance of the ML classifiers with 30-second ECG segments. And we can see that with 30-second ECG segments, the performance is higher than in the 10-second segments. But we can say that it is comparable. So we have gone on, as it is very difficult to say which segment is better here, we have gone to find out the complexity of this, study the complexity. And then from the this table 3 gives us the performance comparison of the 6 different detection methods in terms of computational complexity. We have calculated the model sizes, processing time of each, and also we have presented the accuracy against these to calculate which is the best atrial fibrillation classifier for our work. And we can, from these tables, we have this inference that accuracy is higher for 30-second ECG segment than 10-second by 0.042%, which is almost negligible, we can say. But for 10-second ECG segment, the processing time is lower than, is the lowest with LGBM, and with 30-second ECG segment, the processing time is lowest with multi-layer perceptron model. However, the best performance is given by the naive Bayes classifier. Actually, it is a trade-off between model size, processing time, and accuracy. And we have come to the conclusion that naive Bayes classifier with 10-second ECG segments and model size 1.50 KB gives us the highest accuracy of 99.958 with a processing time of 2.13 microseconds. Now, our work cannot be said to be the best without comparing with other existing works, and we have tried to compare with almost similar kind of works that are available in literature. And from these, we have found that most of these works have not reported the processing time. And this work by Zhao, he has reported the processing time, but the processing time of our method is very, very lower than this method. And then we have also seen that the sensitivity, specificity, and accuracy in our methods and the methods, our methods are higher. And we have also we have also calculated the model size, which is not available in the previous works. From the coming to the concluding remarks, we have employed an amplitude independent QRS technique to identify R peaks in ECG segments using a single feature, that is Shannon energy, Shannon entropy. And then we have obtained an accuracy of 99.958 and 100% with 10-second and 30-second ECG segments. With the processing time of our method is only 5.37 microseconds, and the size of our model ranges from 1.50 to 194 KB, which is also very low. And we can say that this will also consume less power. For future, we want to address the signal quality assessment, or we want to incorporate signal quality checking before atrial fibrillation detection. And we would also like to work on energy consumption so that we can develop a trustworthy continuous cardiac health monitor. For acknowledgement, I'd like to thank ICMR, Indian Council of Medical Research, New Delhi, India, for providing the funds for this project. And as for reference, we have included all the 17 references that we have included in our paper. So thank you.